Hello everyone, welcome back to part 4 of chapter 8. We are continuing our discussion of conservation of energy. I just see I had a little typo there. But this is the conservation equation that we've been using so far. And so far it's worked out pretty well, assuming that all of the forces that we use are conservative. And what that means is that whatever forces that are involved conserve the amount of energy that is transferred or transformed from one state to another. And I was going to write this out, but I'm going to think better of that because I can go ahead and write it out for this one. Our kinetic energy is based off of the mass and the speed of the object. Our potential energy, we currently have two types that we need to consider. The first is the gravity potential. The second involves spring potential, if a spring is involved in the system. And so altogether, if we can keep track of the different types of energy in the system, then we don't have to do work anymore. But this equation only works if we're dealing with conservative forces. And in a real-world situation, having only conservative forces falls under the category of what we call ideal. And if anyone ever says ideal, what they really mean is not really. Because in an ideal situation, we're basically taking the simplest form of the system, and that also refers to the simplest math of the system. And I realize this might not seem like the simplest of math, but these expressions only include the conservative forces. And that means that we conserve what we are calling the mechanical energy in the system. In the previous video, we defined the idea of mechanical energy as being the combination of the two. So this isn't something new that we have to start keeping track of. This is just a definition, a way of categorizing the energies. And these mechanical energies are the good kind of energy, because they allow us to get things done. They allow us to do work. But in a real world situation, which is pretty much every situation out there, we do come into situations that involve non-conservative forces. And these non-conservative forces are going to be things like friction, air resistance, and drag. Drag is typically just the equivalent of air resistance, but with other fluids like water. But all of these forces are resistive forces. And what we mean by resistive is that they resist motion. If we try to move something, these forces are going to resist that motion. As such, they are all going to do negative work. And if a force does negative work, then that work, that change in energy, means that we are going to remove mechanical energy from the system. And if we remove the mechanical energy from the system, that's the good kind of energy that allows us to move things around. Well, if we lose all of that energy, then we can't do anything anymore. And this is why we're constantly having to replenish the energy that we use in mechanical systems, whether that be filling up your gas tank every couple of weeks, or having to pay your electric bill. because all of that energy will be placed into some kind of a mechanical system, but then we lose that mechanical energy due to these resistive forces. And these resistive forces, like friction, are going to start generating heat, or we're going to lose that mechanical energy due to heat. Now, thermal energy is still a form of energy, and if we can keep track of all the energy in the system, which is what we're trying to do here, then we can continue doing the physics. If we can keep track of the energy in all of its forms, then we can tell what's going to happen in these systems. Well, if we take that equation and if we move everything over to the right-hand side of the equation, so if I take the initial kinetic energy, I subtract that over. If I take the initial potential energies and I subtract those over, what I get is a difference in the kinetic energy and a difference in the potential energy. So those are both delta statements. But the combinations of kinetic and potential energies are what make up mechanical energy. So right now I have the combined change in mechanical energy for the system, and it, along with whatever thermal energy is generated in the system, has to equal 0, or rather any net change in energy has to equal 0. And that was the first law of thermodynamics. Energy cannot be created or destroyed, it simply exists, but we can convert it, we can transform it from one type of energy to another, or we can transfer it from one object to another. And that's what we're going to explore in the second half of chapter 9, is how we can transfer this energy from one object to another. Well, this means that any change in the mechanical energy of the system will have to be equal and opposite to any thermal energy that is generated by those resistive forces, like friction. But any change in energy is the result of work. And we already know from the previous chapter that friction forces can do work. We know that the work is always going to be negative. And that's because if we have some object that is moving to the right with some initial velocity, and if there is friction between that object and the surface, there will be a counterforce of friction that points in the opposite direction. As we displace to the right, friction opposes that motion, and we can account for the work done by that friction force by looking at the dot product. The angle relationship between the friction force and the displacement vector is 180 degrees. And so that means, oops, getting too close to the edge of the screen again. That means that we have negative work done by our friction force. Now the friction force itself, by definition, friction is fun. So we have mu k times the normal force. We can plug that in here. But I'm not going to take this any further because the normal force for this particular problem may not be the same as the normal force for another problem. So I'm gonna leave this in its general form until we know for sure what kind of a normal force that we're dealing with in the given system, because those normal forces can depend on things like angle relationships with the inclines. We could also have, say, an additional mass sitting on top of one object, and that increased mass can cause an increased value of the normal force. So we'll save this as it is until we have more information about the particular system that we're dealing with and what kind of normal force we have. But we want to take this information about work that is done by a friction force, and we see that it's negative. And anytime that negative work is done, it means that we're taking energy away from the object. Well, work is not a physical thing that we can transfer this energy to. If we're going to take this energy away from the mass, that doesn't conform to the conservation of energy. We can't just take this energy away and hold on to it. The system has to retain that energy. In other words, the moment friction takes this mechanical energy away, it has to give it back in some other form. And so we're taking away mechanical energy, but then the system is going to return it as thermal energy. So we're going to see heat dissipate into the system. And some of that thermal energy, it may be absorbed by the countertop, some of it may be absorbed by the mass itself, some of it may be absorbed by the surrounding system. But all of that energy is still present in that general vicinity. So we still have all of the energy that we started with. It's just in a different form that we're calling thermal energy. And this is why we need the new and improved equation that we have up here. If we can keep track of all the different forms of energy, then we can continue doing the physics. So an example that we had set up previously was that we have a mass that starts with some initial velocity. I forget now what the value was, but let's just say 5 meters per second. And it's going to slide over a flat horizontal surface. There is friction in the system. There will be a kinetic coefficient of 0.25. The mass will eventually come to a halt at some unknown distance. What we want to know is, what is that distance that it takes for the mass to come to a halt, and how much thermal energy will be generated by friction as we bring the mass to a stop. So to help us out with that, we're going to take our new and improved conservation of energy equation, which says that what you start with is what you end with. And the reason we have thermal energy over here on the right, it's almost kind of like a chemistry equation where you start with your reactants on one side and then you have your products on the other. And that thermal energy is a product of the friction doing work. Well, let's see what we have. We have kinetic energy, initial kinetic energy, in the form of 1/2 mv0 squared. We should probably put in a mass. We could say 10 kilograms. Anything else we might need? Doesn't look like it. There are no springs involved in this problem, so we don't have to worry about including spring potential. But what about gravity potential? We can put in potential energy due to gravity based on the height measured above the 0 point in the problem. Now, the easy way to do this is just to let the 0 point of the problem be at the tabletop, and then our potential energy is 0 to start with. But we're at the same height after the fact. And so even if these two values weren't 0, we would have the same potential energy values on either side of the equation, and they would still cancel out. So that leaves us with a final kinetic energy plus a thermal energy. And we know that because the box is going to come to a halt, the final kinetic energy also has to be 0. Lots of zeros in this expression. But now we see something that should sort of make sense. We started with some initial kinetic energy based on the combined mass and velocity of this object. And all of that kinetic energy is going to be taken away and converted into thermal energy. So we've taken all of the combined mechanical energy that we started with, which in this case it was only made up of kinetic energy, and we lost all of that mechanical energy. Both of these values were essentially 0, and so all of our initial mechanical energy has to have been converted into heat. We have numbers for these. We have a mass of 10. We have an initial velocity of 5. That's going to be, 125 joules. So we started with 125 joules of kinetic energy, and that had to have been converted into thermal energy. So now we also have 125 joules of thermal energy after the fact. So as this block has been sliding, that kinetic energy has been converted into thermal energy, and that energy will then dissipate through the system as heat. But the energy is still there, even though it's in the form of heat. Okay, well, how does that answer the question of how far this mass has to slide? Well, let's go back to the definition of work that is done by a friction force. We know that work is responsible for any change in energy in the system. In this case, we're interested in the change in the kinetic energy. The only force that is really going to be doing any work in this system, if we zoom in, forces involved in this system would be gravity pointing straight down. There's a normal force, and then there's the friction force. And this vector right here just indicates the direction of the velocity, so I'm just going to get rid of that so it doesn't confuse us. But looking at these three vectors, normal force, gravity force, friction force, and keeping in mind what we know about work, in evaluating the work done by any force, there is that cosine relationship. And anytime we have a force displacement vector that are at 90 degrees with one another, cosine of 90 is 0, no work is done. Well, that means that the normal force doesn't do any work because our displacement is to the right and the normal force is up. Likewise, the gravity force doesn't do any work because it's also at a 90-degree angle. The only force that does any work is the friction force. And we already know what that value is. It's right down here. It's the negative mu k nd. All we need to know is what is the normal force for this system. So that's why we said that we were going to wait until we knew exactly what kind of system we were dealing with. In this case, the normal force should just be equal and opposite to the weight. If we do a sum of forces in the y direction, we have normal up, weight down. They'll have to equal one another. So we now have work done by our friction force in the amount of negative mu k mgd. We have numbers for all of these, except d, but that's okay because we know how the kinetic energy in the system has to change. Our kinetic energy started at 125 and went to 0. So we have negative 125 joules for the change in kinetic energy, which has to equal the net work that was done, which has to equal the work done by friction. Work done by friction has a minus sign on it, as it should, just as its numerical value. We can go ahead and drop the minus signs, which is good because when we solve for our displacement, we want to make sure that we're getting a positive value for our displacement, because that positive value is indicative of getting or guessing the right direction of the displacement, even though we haven't put in a reference frame for this problem. But I know everything except the displacement value, so let's solve for it. 125 divided by mu k mg. I believe we had 0.25 for mu k. Yep. And mass was 10. .8 for gravity. Get our calculator. $125 divided by 0.25 divided by 10 divided by 9.8. And this is resulting in approximately 5.1 meters displacement. All right, so there we have it. Whatever amount of work that is done by friction, let's take a look at everything that we did right here. We have the work done by friction was, in our case, the net work done in the system, which was responsible for the change in the kinetic energy of the system. But we also said up here, for this particular problem, since the potential energies canceled out, we can say that the change in the kinetic energy, which was equal and opposite. Well, actually, let me take that a step back to what we said over here. We said that the change in the mechanical energy for the system is equal to the change in thermal energy for the system with that minus sign on it. So what that means for us, since we only had a change in kinetic energy for this system, our potential energies were both 0. For this problem in particular, that change in kinetic energy is the change in the mechanical energy. Okay. Now we have to be careful with this, because this is not going to be true for every problem. A change in mechanical energy has to be the combined change in kinetic and potential energies. In this case, we had a change in potential energy that was equal to 0, and so what's left is the change in kinetic energy. But this change in kinetic energy has to be equal and opposite to the change in thermal energy for the system. So why this chain of equality after equality after equality? Well, now we can put together the two end results, and we can say that the work done by friction, this is just friction, is equal and opposite to the amount of thermal energy that is produced. And if you remember, work done by friction is a negative value. It has to be. Friction will only ever do negative work. So on this side, you have a negative value, which has to equal the negative change in thermal energy. So what does that mean for thermal energy? Well, thermal energy has to be the opposite of the work done by friction, but that means that we're attaching a negative to a negative and we're making it positive. And if I haven't done a good enough job of confusing you, let's just say it this way. The change in thermal energy. Friction is going to do work to take energy away from our object, but then we have to give that energy back as thermal energy. When we take away, when we steal, that's a negative, right? We think of stealing as a negative thing. But then we give back, and when somebody gives you something, like a gift, that's a positive thing. So thermal energy needs to be positive because it's a gain or a regain of the lost energy. And the easiest way to get the value of that is to just say, well, let's use the absolute value of the work that is done by our friction force, and that'll take care of everything. Because the work done by friction is technically negative, but we need that energy to be given back as a positive quantity. And so if we just work with the absolute value of the work done by friction, then we will have the thermal energy of the system. Let's try another example problem. We'll try this one with some actual potential energy values. So for this problem, we're going to do some snowboarding on a half pipe. And so up here we have our snowboarder. We'll give him one of those weird hats. And our snowboarder will start at the top of the left-hand wall with an initial velocity of 0. We're just going to scoot ourselves off the edge of the wall, which will have a height of h. And then we get down to ground level here. And when we get down to ground level, there's some friction between the two walls. In fact, I'm going to try and redraw this if I can, just to make it a little neater. There's not much of a turn. But this is, I know the walls here look very steep. But the reason for that is because I want a flat surface along the bottom where all of this friction can take place. But then I want the walls of this half pipe to be frictionless. So no friction on the walls, but there will be friction along the floor of the half pipe. And we'll say that the floor of the half pipe has a length of L. So both walls have height of H. The flooring has a length of L. Our snowboarder is going to start at the initial location, which I'm going to label E0. So there will be energy associated with that location. That energy will be a combination of kinetic and potential, and we're not going to consider any thermal energy yet, and that's because gravity has not brought us down to the bottom of the half pipe yet, and that means that friction has not begun doing work to generate thermal energy. All right, we'll drop down. Gravity will do some work to increase our kinetic energy. At the same time, it will decrease our gravity potential energy. And when we get to the floor, we slide across the floor. Get rid of this L here. I'll put that down here instead. When we get to the bottom of the floor, our snowboarder is traveling to the right, which means that a friction force will be opposing that motion. And every time we pass through the bottom of this half pipe, there will be work done by friction, and that work is going to steal a little bit of our thermal energy away. So the first time we travel through this half pipe, friction is going to generate a little bit of heat, which will take away some of our mechanical energy, and that means that our snowboarder won't be able to reach the same final height as before, because some of that mechanical energy has been stolen. Well, the whole purpose of this half pipe is that the snowboarder is going to go back and forth multiple times. So the snowboarder stops right about here somewhere. I don't know exactly how high that is, but I know it's not big H. And then the snowboarder is going to fall back down again and travel through the friction zone again. Now, regardless of which way the snowboarder is passing through this friction zone, friction is always going to do negative work. So in this case, the displacement, if we in fact go the full length of the half pipe, would be L, but for right now I'm just going to call that D. But let's say the snowboarder makes it all the way through the bottom of the half pipe again. Well, every time we go through the half pipe, we lose some more energy due to heat, and that means that the snowboarder is not going to be able to make it up the sidewall as high as he did before. So every trip through the half pipe means that the snowboarder achieves a smaller and smaller final height until eventually all of our mechanical energy has been bled away by friction, and our snowboarder is going to stop somewhere. at the bottom of this half pipe. My question is, how far from the left-hand wall does the snowboarder finally come to a halt? And this is a very good problem to show for students that are trying to get a handle on this idea of conservation of energy. And the very first time I saw this problem as a student, I thought, well, I'm going to have to conserve the energy from the starting point and then go to the next point and then go to the next point and then go to the next point. But remember that energy is not chronological. I don't have to compare the energy at the initial site to the energy at E1 and then E2 and then E3. If I want, I could compare the energy between the initial site and the final site without having to worry about any of these other locations. The reason for that is because I don't lose any mechanical energy going up or down these walls. There's no friction there. The only place that I need to worry about is when the snowboarder passes through the half pipe. Well, again, you're probably saying, don't I have to know how many times we go through that half pipe? That's the only way we're going to be able to add up all the displacements. Well, we're getting closer. If we do in fact have to add up all the different times that we pass through this half pipe, let's make things easier on us. Let's knock down that right-hand wall. And we'll let our snowboarder drop down the wall and slide through a friction zone that has the same coefficient of friction as what the half pipe did, and see how far we can get before our snowboarder has to come to a halt. This is very much like the problem that we did up above with the block that was sliding across the floor. We started with some initial kinetic energy, and we let all of that energy be converted into heat. We can do the same thing with this snowboarder, except the kinetic energy that we start with at the bottom of this hill is going to depend on how much potential energy we started with at the top of the half pipe. Okay, well, we can look at a couple of points of interest along the way. We can look at the energy associated with the initial height. If we wanted to, we could look at the energy that we have at the bottom of the hill when we finally get down to the bottom of the hill. I can look at the energy at any point along my journey, but I'm more interested in the energy that we would have when we come to a halt. Up here, we're starting with an initial velocity of 0, so that means there's no kinetic energy at the initial height. Over here, we're ending with a final velocity of 0, which means there's no kinetic energy at the final location. And energy is not chronological. We can compare the energies at the initial and the final site without having to worry about all the back and forth that we have to do through the half pipe. all of that back and forth motion through that friction zone will be accounted for by just traveling as far as we possibly can over that flat friction zone. Well, let's see what we have then. At the initial site, all we have is energy in the potential form of mg big H. I am assuming that ground level will be the 0 point for my gravity potential. And that means when I get down to the ground, when I get down to ground level, I have 0 potential energy. And that should make sense because all that potential energy should be turned into kinetic energy when I get to the bottom of the hill. But then friction is going to start stealing all of that kinetic energy away from our snowboarder and converting it all to heat along the way until we're finally left with no more mechanical energy. And that means the final energy in the system is just the thermal energy. We have no final kinetic energy. We have no final potential energy. So the only energy that we can have at that final location is the thermal energy. Okay, so we're going to take all of the potential energy from the initial location and eventually, through a number of different conversions of the energy through work, which again we're completely bypassing, because if we can keep track of the energy, then we don't have to do work. But all of that potential energy now has to be converted into heat. Well, I have yet to provide a mass for the snowboarder. I have yet to provide a height for the wall. I have yet to provide a length for the separation between those two walls. But this is how physics was meant to be done. It's meant to be done as a general solution. Later, we can provide numbers to work with. But this just tells me how much thermal energy is going to be generated. Ultimately, I wanted to know where, let's see if it use a different color, where are we located with respect to the left-hand wall when we finally come to a stop, after we've gone back and forth through this half pipe. Well, if I can figure out how far the snowboarder could travel in a straight line through the friction zone, then could I compare that to some scalar multiple of the distance between the two walls? Because if I keep going back and forth between the two walls, well, I'm covering a total distance by zigzagging back and forth between the two walls. But if I just compared that to the total distance that the snowboarder could travel, well, then I can use that scalar multiple to tell me not only how many passes through this half pipe I have to make, but also where I'm going to stop. So let's see if we can find that total distance traveled before we have to come to a halt. Up above, we had that short discussion on thermal energy. We said that the thermal energy generated will be the absolute value of the work done by the friction force. And the friction force is right here. It was negative mu k nd where N was the normal force for the system. So we have negative mu K N D. We need to know the normal force as we're sliding through this friction zone, but as we slide through the friction zone, we're sliding over a flat horizontal surface. So at any point, the normal force acting on the snowboarder is pointing directly up compared to the weight of the person, which is pointing down. And the friction force itself will be in a direction opposite that of our displacement vector, which is pointing to the right. So normal force is just equal to mg for this problem. Let's see. Oh, but we said change in thermal energy has to be the absolute value of the work done by friction. So we can throw some absolute value signs around there. That's going to change that into a positive. And now we rearrange for the displacement D, but we have a few things that are going to cancel out. The mass of the snowboarder cancels out. Not only that, but the value of gravity cancels out. Turns out we could do this problem anywhere in the universe. We could go snowboarding on Earth, on Mars, on the moon, assuming there's some snow somewhere. But we're going to rearrange for the value of D, and all we get here is a ratio of the initial height to the coefficient of kinetic friction. Ready for some values? Me too. So let's say that the height of the half pipe was 5 meters. And we'll say that the length from wall to wall, L, is 10 meters. So how many passes through the friction zone can we make? And where exactly between the two walls of the half pipe does our snowboarder come to a halt? Well, now that we have values, the height of the half pipe, we said that that was 5 meters. So we have 5. We need a coefficient of kinetic friction. Now this is a snowboarder, so I want to make this as realistic as possible. I'm going to Google a value for coefficient of friction for snow and a snowboard, if Google can do that. So we'll try this. Coefficient of friction between snow and snowboard. All right, so it does give a range of values. It says that the coefficient of friction between a waxed wooden snowboard on wet snow is 0.1. However, if you have a waxed wooden snowboard on dry snow, then it goes up to 0.4. So just by having a slightly different consistency of the snow causes a change in the coefficient of a multiple of 4. But I want to go with the lower value just so we can actually get a few trips through this half pipe. So we have 5 over 0.1, which is going to equal 50 meters. So the total distance that this snowboarder can travel over the, I guess this is going to be a wet, slushy snow, is 50 meters. We said that that distance could be compared to some scalar multiple of the distance between the walls of the half pipe. There was 10 meters in between the walls, and if L is equal to 10 meters, then 50 over 10 is 5, or N is the number of passes that we can make through this half pipe. So here's what happens. We'll try drawing that again. Make for a flatter floor here. So what happens is that our snowboarder drops down and makes 1 pass, 2 pass, 3 pass, 4 pass, 5 pass. Okay, this came out to be exactly 5L. And that means that we've made 5 passes through the half pipe, but that also tells us where the snowboarder comes to a halt. The snowboarder comes to a halt at the base of the right-hand wall, or 10 meters away from the left-hand wall, as was specified earlier in the problem. So, very good example of conservation of energy and why we don't necessarily have to go back and forth the whole way. We can just let the conservation of energy tell us as we go from one extreme to another what's the necessary displacement required to bring us to a halt, and then we can compare that back to how many passes through that half pipe that we have to make. All right, so this brings us to the end of the material for Chapter 8. I am going to make one more video that will include a couple of more example problems. The next video won't include any additional course material. The one exception to that is that at the end of Chapter 8, the book revisits the idea of power, which in Chapter 7 was work over time. But we now know that work is the change in energy. And there are quite a few different kinds of energy that we can consider. We can have a change in kinetic energy, we can have a change in potential energy, we can have a change in thermal energy. Any one of these changes in energy, if measured with respect to time, will give us a power term. So if we want to know the rate at which kinetic energy is changing, well, we can associate a power term with that. If we want to know the rate at which heat is being generated, well, we can assign a power term to that. Now, are all of these terms going to be equal to each other? Depends on how each of these energies is changing. But the overall change in all of these energies has to equal 0. We have to maintain a constant level of energy in the system. And so even if we had different power terms, just like the change in energy of the system, the amount that the energy changes as a rate overall in the system would also have to be zero. That's not to say that individual types of energy can't have their own power values, but if we added everything together in the system, there has to be a net change of zero. So that's the end portion of Chapter 8. They just bring that back to our attention. If you prefer to use the previous definition of power, you can. If you want to use the newer definition of power, you can. The book does distinguish between two types of power. We have average power, which is the result of a time interval that is large. Remember, with large time intervals, a lot of things can change, a lot of things can happen, and so the best that you can hope for is an average. If you want an instantaneous power, then you need a function for your energy term or your work term that you can take a derivative of with respect to time, and then that will give you an instantaneous power. All right, so stop back for one more video with example problems with power and conservation of energy and thermal energy.